Hi, good morning. This is our project for the Advanced Power System, Dr. Ashraf Ali Khan. Our project topic is hybrid off-grid renewable energy system for remote communities, Bella Cola, BC with micro hybrid integration. I am Patum and my colleague is Lynn. This is our content. There are four major topics, which are introduction, background, and system modeling will present in May, and the other part of stability and control system and conclusion future part will be produced by the link. Part 1, introduction and background. Belacola's current electricity system is predominantly diesel-based. This leads to three major issues: high fuel cost, greenhouse gas emission, and vulnerability to fuel supply disruption. Renewable energy offers a promising alternative, but relying on a single renewable source is not practical due to resources variability. For example, solar energy is limited in winter and wind energy can be intermittent. To overcome this project, propose a hybrid system that combines solar PV, wind turbine, micro-hybrid generation, battery storage, and diesel backup. Among these sources, micro hydro plays a key role because it can provide continuous base load power, especially in a region with contained river flow like Bella Cola. The main objective of projects are to reduce diesel fuel consumption, to lower the levelized cost of energy, the maintain reliability electric supply under varying conditions, and to evaluate the system robustness using sensitive analysis. Next part will be system modeling and main contribution. On this slide, I explain how the system was modeled and how the load demand was estimated. Renewable sources data such as solar radiation, wind speed, and temperature were collected from NASA Surface Meteorology and Environment Canada, ensuring reliable long-term data. The bar chart shows the monthly stream flow of the Belacola River from the May 2024 to 2025 April. We can clearly see how flow rates during summer months, which makes the microhydro a strong candidate for base long generation. On the right side, I show the load demand estimation. The community's average daily energy demand is about 21,000 kilowatt hour with a peak load of 4.32 megawatt during winter months. Mainly due to space heating and lighting, this load profile strongly influences system sizing and motivates the use of hybrid energy sources. This slide shows how different hybrid system configurations were created using Homer Pro. Six system models were developed using combinations of solar PV, wind turbines, micro hydro units, battery energy storage, and diesel generators. Each model represents different strategy ranging from fully renewable system to hybrid system with diesel backup. The goal was compare performance cost and reliability across all configurations. On the right side, I have summarized the sensitivity analysis parameters. These include this fuel price variation from $1.2 to $2 per liter, a 20% reduction in river flow to simulate dry year conditions. The table also lists different micro hydro turbine options showing their rated power efficiency, lifetime, and head time. All turbines considered are the suitable for low head river conditions, which matches the Bella Cola site. This slide presents the main result obtained from Homer Pro. The table compares all six system models in terms of renewable fractions, diesel contribution, levelized cost of energy, and excess electricity. We can see the model 4 provides the best balance. It achieves a renewable fractions about 77.7%, relatively low diesel usage, and the levelized LCOE at 0.308 kilowatt hours, which is highlighted in red. All right, although Model 6 has a highest renewable fraction, it also produces a large amount of excess electricity, which increases cost and reduces efficiency. Overall, these results show the integrating microhydro significantly reduce diesel usage and energy cost, while also improving load matching. This slide focuses on the sensitivity analysis, which evaluates how the system performs under certain uncertain conditions. On the left, we see the impact of 20% reduction in river flow. The renewable fraction decreases, diesel usage increases, and LCOE rises slightly. However, the system still remains operational and reliable. On the right, the table shows the impact of diesel fuel price increases. When fuel prices increases from $1.2 to $2 per liter, net present cost increases by about 15%. Annual operating and maintenance cost rise. LCOE increases noticeably. This demonstrates that while the generation profile remains similar, the economic performance is highly sensitive to diesel fuel price volatility, reinforcing the importance of maximizing renewable presentation.
Okay, this is Lee speaking, and I'll do the part 3 and part 4. Part 3 is about stability and control analysis. So we add subsystems. The RMS phase-based subsystem generates three-phase currents based on reference magnitude and phase. It behaves like a real inverter output, ensuring proper synchronization with the microgrid 60 Hz AC bus. And that's the input layer and control layer. RMS captures frequency and voltage dynamic more efficiently. PV, wind, and battery are controlled through active power references, which are converted into three-phase current injections. Diesel serves as the main voltage reference source, like the system frequency through the AVR. So that's the full design hybrid power system. This structure places all generation units on a shared AC bus, allowing coordinated control and smooth power sharing between diesel, hydro battery, and inverter-based renewables. So we considered two disturbance scenarios. This is for part 4. So that the result from the scenario 2 is in the part 4. So part 4 is about conclusion and future work. The conclusion through Homer is that among the 6 configurations, Model 4, which demonstrated the most favorable balance, the LCOE is the lowest among all. Diesel generation has reduced, renewable fraction achieves almost 80%. Meanwhile, excess electricity kept moderate. Sensitivity analysis also confirmed that wind resource availability and fuel price are the most influential parameters affecting system economics. These results indicate that a properly balanced mix of renewable and dispatchable units can economically sustain remote communities such as Balakola, with reduced dependence on fossil fuels. So that's the result from dynamic simulation. For the scenario 1, we increased 20% load at 10 minutes. And for the active power, right after the load increases, the battery jumps up almost vertically because of the inverter fast frequency support. For the reactive power, this occurs due to the interaction between diesel generator and inverter. So both P and Q curves quickly settle to a new stability. And for the scenario 2, the wind power suddenly drops by 50%, and the system responds like diesel output increases immediately to replace the lost wind sources. Batteries provide temporary support, systems return smoothly to steady state. This shows the control system is capable of handling renewable variability. So for the future work, we also realized that the resource load is mismatched. The Balako's river flow peaks in the late spring and summer, while the peak energy demand occurs in winter, primarily due to the heating needs. Meanwhile, batteries can particularly buffer this mismatch but may not fully eliminate the diesel need. So in winter, a rule-based mismatch where batteries serve mid-peak and detail fill deep gaps is necessary. Also, for the future work in Simulink, we'll focus on implementing real-time control to emulate field conditions, as well as seasonal modeling to capture hydro and solar variability, integrating predictive energy management can further enhance dispatch optimism, reduce diesel runtime, maybe supporting better close long-term transition towards with a fully renewable energy system. So that is all my project. Thanks for listening.